Good morning. Am I audible? Yeah. What about online participants? Am I audible?
Yes, sir.
Yes. Thank you. So let me start with what you have discussed in the yesterday's discussion. So hope you might have already seen what neural networks are familiar with what neural networks are. And you also might have discussed an overview of our basics of convolutional neural networks, right? So I assume that you're all working in this area, are familiar with machine learning. With this context, I will introduce application of convolutional neural networks to computer vision. That's the major objective of this talk. I will start with giving more details of convolutional neural networks. Essentially, I will be discussing on some of the key aspects of learning in convolutional neural networks, learning in deep neural networks. So, what are the differences between learning a simple neural network or a shallow neural network with very few layers versus learning a neural network with hundreds of layers or thousands of layers. So what are the differences? And I will also try to give some highlights of how these convolutional neural networks have evolved over years and different applications in which these are used, are applied. Subsequently, I will be discussing on some of the evolution of convolutional neural networks in terms of different computer vision tasks for different computer vision tasks, such as object detection, tracking, and 3D reconstruction, few other computer vision tasks. And I will also be discussing on one of the well-known variant of development in this deep learning, that is generative adversarial networks. Also, feel free to stop me at any time or at any point if you are not very comfortable or did not understand what I am trying to convey. Probably after some discussion, I also will try to give a pause and take your questions. So probably what I would like to start from the perspective of computer vision. Of course, that I prefer, I being from the computer vision area. And also I see that how the evolution of computer vision has influenced the evolution of convolutional neural networks or the deep learning area. And I will also try to give you some hints on why the convolution aspect is so important in learning of neural networks, in development of neural networks as such. So let's start with the understanding. Of course, you may know images well, or you might have seen what image is. Image is nothing but a set of pixels. So for a computer, the image is a matrix or an array of pixels. It's for visual understanding of humans and us. For us, it makes so much of sense in terms of say objects being there, context being there, and so on. But for a computer perspective, it is just a matrix or a set of pixels. Now the challenge for computer vision is to make some inference out of it. So to make some inference out of images, out of scenes, videos, and so on. Of course, alongside you may have other data, metadata, essentially maybe in terms of either voice or in terms of text or many other forms to make better inferences. But essentially the problem in computer vision is to see or understand out of the picture or videos. So then what are the major features? See, the evolution of computer vision has happened with image processing. So given this image, what are the salient regions or salient details that we should look at? Say the objects, for example, objects are defined by their boundaries. So how do we get the different objects and their boundaries separated? So one of the very well-known process for that is finding edges, where it separates or it highlights the object boundaries and subsequently separates the objects. So the discussion, how we find edges is essentially through the process of one of you answer how we find the edges?
Filters.
Huh?
It's a high pass filter.
Yeah, high pass filter, or can you give a even better picturization of how do you find the edges in an image? Edges are essentially where intensity variations are very high. Okay, where the gradients are very high. So how do we find them in an image? So assume that I have a scene of this class. I want to separate each desk and want to count how many desks are here. Okay, how do we do that? What is the first step in that?
Segment.
So this answer is very important for understanding subsequently the convolution neural networks. So the hint is
Kernels.
the kernel. With kernel, what do we do? We do with kernel. So for example, if I want to find out the gradients where there is a white to black transition. Okay, what I want a kernel also which imitates this image. That means the kernel also and should have a black region. Then if I correlate with this kernel at any different locations of the image, what will happen? I will be able to see wherever the white to black transition happens, there the correlation becomes maximum. Okay, so essentially the correlation with the kernel will give us the regions, highlights the regions of sudden transitions when the kernel is also off with sudden transition, right? This process is called, this is of course in mathematical terms or statistical terms, it is called correlation, wherein we try to identify a region in the image which is quite similar to the patch I have considered, or quite similar to the kernel or filter I have considered. If kernel is of having a peak in the middle and then having a depth in the other regions, that is 0, all regions are -1 in all regions and +1 in the middle. Then if I correlate with that over an image, what do you think I will highlight in the image?
All the dots.
All the dots. All the points where there is a point targets or point very sudden jumps, either to positive to negative or negative to positive. So if I want to identify a object of interest, what I have to do is to figure out a filter of that nature, okay, and then correlate it. In terms of statistical or in terms of mathematical terms, this operation is called correlation. In terms of system sense, it is called convolution. Convolution is nothing but you flip the kernel, okay, whatever kernel, that means if you have a kernel of, say, as you can see in this slide, here you have two kernels, for which will find the horizontal and vertical edges. See, this will find, for example, any horizontal edge, the first kernel. Second kernel finds any vertical edges. Okay, so because this kernel itself, if you see, it is negative, okay, and then 0 and transition from negative to positive. So it itself looks like an edge, right? So when you correlate with that or when you convolve with that, you will find all horizontal edges. This highlights all these horizontal edges, whereas this will highlight all vertical edges, right? So essentially, this convolution is nothing but flipping the kernel and doing correlation. That means if you just put here horizon and flip the kernel, flip in xy and this way. Okay, so both sides, you just flip mirror image completely and that you correlate. Okay, that is essentially convolution. So convolution is essentially an operation to identify the regions of interest through kernels. Okay, so that's what is exactly done in convolution neural networks. The difference between neural networks, feed-forward neural networks and convolution neural networks is, we will come to that in more detail, but essentially is the feed-forward neural network or artificial neural networks, which we call ANNs or FNNs, doesn't have, okay, a convolution operation in it. Okay, it is essentially there also is correlation is there, but in a very one-dimensional sense, not in multi-dimensional sense. Okay, but whereas here we can identify our own dimensional filters, okay, or kernels, okay, and then they can be used to extract the highlight the features of interest in the image. Okay, that is a key that is a key development in convolutional networks, and that has been widely applied, and the evolution of image processing happened through that. So in image processing, if you want to find edges, you fix the kernel here. Okay, so you're fixing the kernel as like finding edges. Okay, similarly, as I mentioned, for block detection, which is very well known as Laplacian of Gaussian operator. Those who are a little bit familiar with computer vision or image processing. So Laplacian of Gaussian operator looks like a Mexican hat. Okay, there is a hat in between and then comes like this. It's like a block. Okay, wherein there is a peak and then tap. Okay, so if you convolve with that, wherever, say, if I want to find it, identify blood cells in an image. Okay, let it be red blood cells or white blood cells or whatever. So if red blood cells are of smaller size and white blood cells are of bigger size, I want to identify where the red blood cells are, where the white blood cells are. Okay, what do? I take a Laplacian of Gaussian operator, a Mexican hat with a smaller block. Okay, that means smaller inner circle. Okay, and then I will convolve. I will be getting red blood cells. If I fix the sigma being higher, that means sigma of the Laplacian of Gaussian with a wider block, then I will be getting a wider Mexican hat. I will be getting white blood cells like that. So if I want to identify a particular object shape or particular features of the object, we design the filters in image processing or in computer vision. Okay, that is what have been evolved. So this is one very key aspect of filtering or convolution that is used in image processing for different feature extraction states. Essentially, as you can see, this is the process of convolution. Those who want to familiarize themselves with the convolution networks has to know convolution well. That is being repeatedly, it is applied for thousands of times or millions of times in convolution networks. So what convolution is, essentially you have a kernel like this or filter like this. Okay, and we are element-wise multiplying on the image patch or wherever the feature map. Okay, it may be on different things we may be applying, but essentially we have a bigger image or bigger feature map, okay, on which a kernel or filter, and we are performing convolution at different locations of the image or feature map. Essentially, what convolution means, it is as you can see, this is already flipped kernel, element-wise multiplication is done here, and then you put all of them, sum them, and put at the center. Okay, so this center pixel now is replaced by the element-wise multiplication of the image patch and the filter in that region, overlapping region. Okay, that is what is convolution essentially. That is done not only at one pixel, it is done at all locations. Okay, in the image. Okay, same thing repeats. Again, it will be centered here, the kernel will be centered here, element-wise multiplication happens, and then put the value there. Okay, so that you keep doing it each pixel, that is process of convolution. Okay, so fine. This is not only for feature enhancements. This is also modeled for different different tasks in computer vision. Say, for example, if a person is moving or a car is moving, okay, moving fast. I have captured it with a camera. Okay, if I take a frame, what will happen? The car image looks blurred or smeared. Okay, what happens is, essentially in camera, when I capture an image, what is happening is, I am in the camera, there are CCD sensor elements. Okay, so what we are doing is essentially, each of the sensor will look at a small region in the space and it averages the intensities in that region and puts it as a value as a pixel. Okay, that is what we mean by capturing an image. Okay, so if I capture an image with 1 megapixel camera, what does it mean? So it is 1000 cross 1000 pixel sensor elements here. Okay, so 1000 cross, each sensor element captures a small region in space, some mm cross mm, okay, and puts it as a value. If the region it captures is of black region, okay, what I will be getting is essentially a torque or zero value there. If the region I'm capturing is white, bright, okay, I will be getting a value of 255 or 200, something like that. That's what we look as the image. Okay, so now when the car is moving, what happens? The region of car, okay, in the exposure time, that means there will be some time in which it looks at a small region and puts it as a value, right? So in that exposure time, the car has moved, okay, by some extent. So instead of averaging a single region, it averages a set of regions, okay, when the car is moving. So and then it averages all that regions and put it as a value. Okay, so what will happen? That's why it looks as black. Okay, if the car has white and black, okay, regions, those gets averaged and put as a value. So it looks like a smear. So that's what happens in motion when we capture the objects in motion, and this is referred to as black in image in computer vision. Now, what is this? How is this process related to convolution? So why did I bring in this aspect? Okay, in discussion of convolution. Yeah, anyway, what is happening is it is averaging over 10 pixels and putting a value. So there is a kernel of 1 by 10, 1 by 10, 1 by 10, 1 by 10. Okay, that makes element-wise multiplication in that region and puts a some value here. So here in the image capturing itself, the convolution is happening. Okay, in the sense that there is a natural phenomena of convolution in like while acquiring the image itself. Now, if I want to, what I want to do now, I want to get a blur-free image. So, usual problem of deep learning is, so given a blurred image which is acquired in real cases, how do we get a blur-free image? Okay, so if I want to get a blur-free image, I have already did a convolution here with the averaging kernel. So, I have to figure out a kernel which does the deconvolution. Okay, so I have to figure out another kernel which does an inverse operation to this. Okay, so that is the challenge, or that is the problem of finding another filter. Okay, that is, for example, if I have done already smoothing, I want to enhance edges. So what I do now? Already the regions wherever there is a transitions are already averaged. So now I want to highlight the regions of transitions. Okay, I may apply some kind of edge enhancing filter. Okay, something like that. Okay, so essentially what I would like to bring in here is many of the operations either in naturally acquired images or in processing of images for feature extraction or modeled as convolution operation. Okay. So now, of course, computer vision is a vast field. Okay, it has many other things. Now it is in fact dominated by deep learning and the developments of deep learning. The other important aspect in computer vision development is see, I want to count the object is here is in image processing, the input is an image and output is also an image. Okay, so we want to process and show them with enhanced features or extract some information and show them as on the image only. But in computer vision, the problem is to make inference out of it. Okay, so what inference do we want to make? So for example, here in a class, we want to count the number of persons. Okay, or here we want to count the number of razors. So how do we do that? Is a challenge. So any idea on how we can do that? Of course, online participants also can discuss or answer. Okay, segmentation. How do we do segmentation? So hope given that deep learning has already been introduced or maybe familiar to some extent. Okay, doing segmentation in one stretch using some network is can be done. Of course, that we will discuss it later. Okay, but we would like to get an intuitive idea on essentially how difficult they are and how this now does. Okay, that process. So that you will also be using. In fact, if we see the developments of the convolution networks for computer vision, many of them have been leveraged from the developments of computer vision. Okay, I will be discussing in the subsequent discussions how of course they may be put in a different framework of neural networks, but they're all essentially the ideas from computer vision. So having familiarity here will give you more ground or more strength in terms of understanding and as well as development. Also, if I want to count the say number of razors here, okay, what essentially one way is you find out a filter. Okay, that looks like a razor. Okay, and then try to convolve. So here anyway, finding edges is easy for us. So once we find edges, see all razors may have a say kind of a border like this. Okay, assume that I figure out a filter which will have roughly of that sort. And then I can convolve or correlate and try to find the number of razors. But the challenge here is the razors may not be aligned. Okay, they may be in different directions. Okay. And may not be at same scale, different scales. Okay, and some may be occluded. Occluded means one hides behind other. So all these challenges will come in real situations. Then how do we handle this? So usual procedure is, if you have a template, this is referred to as template now. Okay, whichever we want to identify in a bigger image. Okay, the small, template or the kind of features we want to extract are embedded, are considered in a, or put in a template now. Okay, which looks like a border of razor like this. Assume that. Okay, now this template may appear in different angles. Okay, and different scales. Okay, and then different maybe viewpoints and so on. Okay, so now in this situation, so what do? I have single template. I make itself at different scales. I can make it at a smaller scale, bigger scale. Okay, if I know the template, I can make it, right? So if you want to identify blood cells, for example, red blood cells. Okay, some small, bigger, and so on. Okay, so I can I can resize. Okay, the template itself. Okay, there. Similarly, if I want to identify a particular chair, for example, in the class. Okay, so some chair may be closer, some chair may be farther. If I have only chairs, I can make a template of it and then make it at different scales. Okay, so usual procedure is have a template, bring it at different scales. Okay, different orientations. Okay, and then try to do convolution with all templates. Okay, from a single template, I have created large number of templates and do convolution or correlation here. Okay, so that is what is conventionally done, but that requires several templates and correlating over the whole image, right? That is very computationally intensive. So what people does is, see, if I have a bigger image, if I want to find the number of persons in a classroom, okay, so why should I search over whole image? First, let me identify where the faces are. Okay, then I want to recognize who are they. Okay, if I want to recognize who are there in the class, or if I want to make an automated attendance, let me first recognize the regions of faces. Okay, and then let me recognize the person. Okay, each face. Now, initially for detecting the face regions, okay, I may need to do a little bit of X-axis search. Okay, or I may find out interest points or key points in an image where the information is there. That is usually done. That means where to look. Okay, in the image is a very important problem that is addressed in computer vision. Where to look means where there is a high probability of information. These are called regions of interest. Okay, so now here key points are the regions of interest where there is a intensity variations around that point. Okay, are the regions of interest, because if there is a uniform region, okay, that's may not be very, there may not be any objects. Object means having variations in the intensity. Okay, so within the object there may be uniform regions. That's okay, but I want to find out the key regions where I can get hold of the object itself, right? So those are usually identified by finding the key points in an image or finding the interest points in an image where there is a variation. Say if I see a small region, if I see the intensity variance of the pixel intensities in that region. Okay, so if the variance is 0, what does it mean? If I take a small patch, okay, 5x5 patch I have taken, and then I have seen in the 5x5 patch what is the variance of pixels or intensities in that region. Okay, it is 0. It turned out to be 0. What does it mean? It means it is a
same color.
Same color or same intensity. Not necessarily 0. It can also be 0, but not even all 255. 5x5 region, all 255 also has a variance of 0. Okay, so essentially it's a uniform region. There is not much information for me to capture the object. Okay, if the variance is very high, okay, very high value, then it means that there is a object interest points there are key points to capture the object. So those are identified usually. Though around those key points, we want to extract some information later. Okay, so what to look comes next. Okay, this is the whole computer vision development has happened with these aspects. That means where to look and what to look. And what to look means how to represent that information around that point. Okay, so now usually that is done. One of the very celebrated methods is scale invariant feature transform. Okay, which gives the key points at different scales, and that is applied here. Okay, as you can see, it finds different key points in an image. Okay, and around these key points, we want to capture information and do something. Here what we want to do is we want to make a panoramic view. Okay, assume that we have a snaps taken at different viewpoints or angles. Okay, and there is some overlapping region between them. I want to merge them or make a big panorama of the scene. Then what do? I find out the overlapping region first. Okay, are the key points, all key points in this image, all key points in this image. Want to find out which key points are same between these two. Okay, that means I have 100 key points here, 20 key points or 30 key points here. With this 20 and this 100, I will try to match and say that among this 10 key points are same as this 10 key points. That is referred to as correspondence. Okay, or finding the similarity or finding the match. Okay, template matching is if I take a template around it, it is called template matching. Otherwise, correspondence of key points. Okay, this is applied in all computer vision tasks. Find, of course, wherever key point based methods are developed or feature based methods are developed, they will start with features or otherwise directly regions. Okay, but over them, the template matching or the correspondence is essential for almost all computer vision tasks. Also, this is what is identify key points in this common region. Okay, and then this is all the common region as you can see, and they have created a panoramic view with some kind of transformation. We assume that there is some mathematical transformation like rotation or whatever between these two and then alignment. Also, the other pioneering work in computer vision is face detection by Viola and drones. Those who work on face recognition detection might have come across this. So here also the key idea is, as we discussed, see if I want to find faces. Okay, I want to generate a template like a face. Okay, and then want to correlate. Okay, and identify the regions of face. Okay, which are the key templates that will help us to identify the face? Essentially, the eyes region. Okay, and then this chin region and so on. So where essentially, as you can see here, okay, the eyes are dark and this is bright. Okay, and this is one template. Okay, which will easily help to identify the eyes region or face region. Similarly, the nose brighter and the eyes darker. Okay, essentially, of course, the Viola-Jones method comes up with a lot of features, a lot of templates. Okay, which are generated with the plus and minus operations. Okay, only 1 and minus 1 are. The template only has only ones and minus ones. Okay, it is easy to make multiplication as addition there. Okay, and they have come up with a very fast method for face detection. It is one of the very celebrated methods. I think even now it's used in cameras. So hopefully the deep learning still I don't think has replaced it. So it does in real time, almost real time, 15 frames per second or so. And it generates so many of this kind of templates. And there is a mechanism to identify which are the good templates among them. Template in the sense that which filters are good. Okay, and then which will extract better features. They identify that these two are good. These kind of filters are good. And this naturally also gives a good meaning. Okay, so and then once we identify, say if a given whole image, if I want to recognize persons, at one stage it is not easy. Okay, at each patch, if I want to take whether it is a face or not and then recognize. But this will enable us to detect the faces very quickly. Okay, in a fraction of a second. Once I detect where the faces are in all our cameras, if you position, okay, you can see our faces with a bounding box, right? So that uses this. Okay, and once we position that, then based on that region, I can recognize who they are. That is easier. Okay, we can crop and then from the, say if I have 1000 cross 1000 image to 20 cross 20 patch, okay, to recognize a face, that will be much simpler and it is already localized. Okay, so this is, this also, as you can see, this is also a convolution operation happening here. Okay, so the not just the detection of corners and edges can be done with the convolution operation. Also, objects of interest can also be identified using efficient convolution operation. But the problem here is, if I want to highlight the edges, we have figured out one kind of a kernel. For corners, we said another kernel is required. For face, another kernel is required. Now the question comes, for my application, which is the best kernel? Okay, that is essentially very well solved by convolution neural networks. Okay, we'll see that. So once we find the key points or the regions of interest, then how do we represent them? What to look in that regions? okay, is the other set of methods that are involved in computer vision. There are several this is called feature extraction, essentially in machine learning terminology. That means, given a region, what features describe, what attributes describe them better. So, for example, if I want to classify aeroplane versus birds, okay, one set of features are important. Their length, okay, width, shape, okay, are important. Say faces, for example, if I want to classify, okay, length, width, there may not be much differences. Some kind of color and position between eyes and nose, few other things. Okay, so in blood cells, it is completely different features. Color is more matters there. So like that, each like application demands different set of features. Okay, now which are essentially in image processing or computer vision, which are the features which are okay good or common in several applications, and which are, see, good features. What do we mean by good features? If I say the features are good, what do we mean by good features? Say face detection, face recognition I want to do, or I want to classify 2-3 different kind of faces. Okay, or 100 students in a class, I want to recognize them, each of them to their own ID. Okay, so what are the good features? Or when I say the features are good, what do we mean? Chair I want to detect anywhere. Okay, or if I want to detect trees, okay, from a natural image. What are the good features means which are invariant, which are not variant to, okay, the photometric and geometric variations. Essentially, if I want to if I capture a person either from the far or from the near, I should be able to detect the face, recognize the face. Okay, the person may be tilting like this or like this and so on. Okay, there can be view variation, there can be scale variation. Okay, or there can be color variation. Okay, in all these aspects, I would like to differentiate or extract the features which are invariant to that. So, for example, if I want to identify a person, if the person is far, he looks very small. Okay, and view can be from different views. So, these are all geometric variations we call. Okay, geometric means in terms of the geometry itself, it is different. Okay, the photometric variations means, say I may take during say night time or daytime or different weather conditions, okay, and so on. Okay, different lighting conditions. So all these influences the photometric way or the intensity variations. That is photometric variations. So I want to have features which are invariant to geometric and photometric variations. Essentially, the very well-known features that are used in computer vision are any idea on which are the features very widely used? So in images, if I want to extract features, okay, and say that this person or not a person. So histogram of orientation gradients. Okay, these are very well known. Those who would like to have a little bit of understanding of grip of what essentially we want to represent an image information as. Okay, this gives a very nice idea. Essentially, as you can see here, this is essentially comes from the gradients, that is edges, gradients means edges, and orientation of gradients, that is angle of edges. Okay, and then, but I want to pool in a local regions if I want to represent the whole image, okay, with some kind of a feature. What I look for is a histogram. That means I say that this image is dark, this image is bright, or this has all intensity variations. This has two objects in an image. That means histogram is my bimodal, in the sense that there is a background, there is a foreground with high color intensity distributions. Histogram means you have intensities in this x-axis, okay, and then y-axis is probability of intensity and the number of occurrences of intensity. Okay, so you have actually 0 has occurred for 20 times, okay, and then 50 intensity has occurred for 500 times. That is essentially captured from 0 to 255. That is called histogram. If I have a clear background, some background and then foreground, then what will happen? Foreground object may have different color. Okay, for background object may have different color. So there will be there will be two peaks in the histogram. Okay, around 50 if background object is dark, around 50 it may have peak around 50, and foreground object bright with say 100 or 200, it is another peak around 200. So like that. So if I want to separate red blood cells and white blood cells, if I take a histogram, okay, red blood cells will be darker in grayscale. Okay, white blood cells will be brighter. I can easily separate like that. Okay, so these are all the basis of segmentation as well and feature extraction. So essentially what histogram of orientation gradients does is, it takes a some region. Okay, in that region it finds the edges first and angle of edges. See, angle of edges gives us shape information. Why shape information? Because see, if I go only by intensities, it is not invariant to intensity. Is it not? So that means if I have an object, okay, if he wears white shirt versus black shirt, okay, I should not get different features. Okay, so edges to some extent normalizes it. Angle of edges makes even more. That gives a shape of the object. As you can see here, angle of edge is straight 90 degrees here. Okay, it gives the person is standing. Okay, so that is that we want to capture in each of the local regions. What is the angle of edge? Okay, that is orientation of gradients, and make a histogram. Why histogram means I don't want to base with a single angle. I want to take angles in this region, and dominant angle in that region may be 90 degrees. Okay, if I see this, say if I take 10 class 10 or 11 class 11 paths here, all will not have 90 degrees angle, but many of them will have 90 degrees angle. Okay, showing that it is straight. Okay, so what I do is I take a patch. In that patch, I take the angle of edges. If you see here, angle of edge is horizontal, here is 0. Uniform region means angle of edge is 0. The edge itself is 0, magnitude of edge. Okay, so magnitude of edge is used to multiply the angle of edge so that they get the strength of the angle. So in uniform regions, it is 0. So, and here it is 90 degrees, here it is 45 degrees, as you can see here. Okay, hope you are able to see my pointer. So like that. So if I take a region, in that if I take the dominant angle, that is essentially got by histogram. Essentially gives what? Dominant intensity. If I take histogram of angles, I get the dominant angle. So that is what is essentially done in histogram of orientation gradients for feature extraction. These are in fact very celebrated features before this deep learning era. All used to depend upon histogram of orientation gradients. And of course, there are several developments of these features. Okay, so now this is applied initially for the human non-human classification. Also, these are some of the large scale works in computer vision. And the point I would like to make here is, in each of these things, even if I want to find histogram of orientation gradients, what am I doing? I'm doing convolution first. Okay, and then extracting edges. Of course, I am there using angle of edges. So on the top of it, some nonlinear operation. Okay, I'm getting the angle of edge. Okay, so essentially what I would like to highlight is for key point identification or for regions of interest identification or for feature extraction. Okay, the convolution operation is the key. Okay, and this has been widely used for different applications in computer vision. Now let us see, this is a face detection that is done in lab setting. This is in classroom. Some of the students have developed some automated attendance systems as well. So probably I will show some of the results at the end on what some of the students have done as projects or research in our group. So this is, of course, this is called visual tracking. Here, this is another computer vision task. Previously, whatever we have seen are essentially classification we have seen first from the features. How do we separate objects? So, for example, detect objects or give the object boundaries. Given the features, how do we distinguish the objects? That is classification. And then, given the features, we have seen an application of panoramic view. Okay, also given these features, segmentation also can be done, that we will see later. This application is to track an object. So, for example, if a car is moving or an object is moving, what we want to do is we define a template first. I want to track a particular person. That means I give a template of the person. And wherever he is, I want to locate his or localize his region. Okay, in an image or a video, mainly in a video. Okay, that is referred to as tracking. Okay, so here the track is given or the target object to be tracked is given, and then what we want to do? We want to do a kind of, say, in first image, where is this person? Second frame, where is this person? Third frame, where is this person? So what is essentially we are doing here? In each frame, we are trying to do a kind of a correlation or convolution with respect to the template. template here is not a kernel or a filter. Template here is a person itself or the object of interest itself. So if you want to track a car, okay, car itself is a template. Okay, car itself is a to be used as correlating object. Okay, of course I can do correlation directly with the car image. Okay, car patch here. Okay, car template here and in a whole image, frame versus frame. Okay, and to locate where it is, or I can extract features of this car. Okay, and as I mentioned, different features can be extracted. Okay, edges are some kind of features in Razor application we have seen. Okay, edges are features. Okay, in previous human non-human histogram of orientation gradients are features. So I extract features of the car template here and put it here. Extract the features of the image, put it here. I apply the correlation instead of in the image space. Okay, I apply the correlation in the feature space. Okay, that is also can be done. That is essentially is done. Okay, for identifying the objects better. And we do that from frame to frame. That is called tracking. Okay. However, each of the tasks has some slight inherent differences. But what here we want to do is, we again want to say, given a template, at each region in the image, is there a template or not? Okay, so I am essentially doing a classification from the template patch, using the template patch at each region in the image. Okay, for first patch I take in the image and say whether that patch is a template of interest or not. Okay, it's a binary classification in terms of classification. If you look at car, if you want to identify, okay, I take a car template. I have a bigger image. Say, for example, if you see here, I want to identify this person. What I do now, I have taken this person template. Okay, I am trying to see at this location is there a person or not. Answer is no. So it's a binary classification problem. And at this location, no. At this location, no. But at this location, yes. Okay, I say that the object is here. Okay, like that. So similarly is the case. So what I would like to bring in here, another point is, many of the computer vision tasks are posed as a classification problem itself. Okay, even though they look like object detection, we call, okay, and then tracking we call, and few other things. Okay, so different tasks we perform. Okay, of course, not all, but many of the computer vision tasks can be posed as a correlation problem or as a classification problem. Correlation means what? I want to say yes or no for the template. Okay, being matched or how much extent it is matched. Okay, that is essentially classification. Fine. So now let's come to the aspects of machine learning and to neural networks and convolutional networks. So far, any quick questions or doubts? From online participants also?
Excuse me, sir.
Sir, there is one question.
Yeah, please go ahead.
Not that. Okay.
Yeah, please. Yeah, please tell.
Hello,
Yeah, please tell. You are audible.
am I audible?
Yes, please.
Sir, my question is like there is a technique we are using CNN in the compression.
Right.
If we are going for the CNN with the feature extraction, then how it is recovering all the data from the feature extracted data, sir?
Okay. So probably I will.
It's a reverse process, I think.
Yeah, I agree. So it can't completely extract the whole information unless it is encoded in a particular way. In some cases it can extract if it is essentially in conventional methods. We say lossless or lossy compression. So if there is a direct relation between the compressed domain and the original domain. So essentially what we do is, those who are familiar with Fourier transform, we represent a signal in Fourier transform. For example, if we represent a signal in Fourier transform, then what happens? Most of the image, if you see in image space, it may have 1000 cross 1000 pixels. But if you see in frequency domain, the image has more uniform regions. Okay, and all these uniform regions comes as just a DC component, nothing else. Okay, low frequency components. And wherever the edges are, okay, are transitions, sudden transitions, they will be at different frequencies. So if I see in frequency domain, only few regions or few frequencies will have higher magnitude, remaining all will have almost zero magnitude. So if I, without thresholding, if I just only look at non-zero components in frequency domain, assume that I have a 1,000 samples in time domain. Let's to understand, let's take one dimensional. 100,000 samples in of speech signal. Okay, and I have taken a Fourier transform. It will also have 1,000 samples. Okay, if I take discrete Fourier transform. But in 1,000 samples, only say assume that 600 samples has non-zero magnitude and 400 samples has zero magnitude. If I want to transmit, what I do? I won't transmit other 400 which have zero values. I say that these locations have zero values or these locations have non-zero and this is the value. Okay, so in that way what I can do is I can reduce the number of bits, and that kind of thing is called lossless compression. There we can recover full information. But wherever there is a, see what we do in lossy compression is all the frequency domain, all the frequencies having less than some magnitude will be, I will put them as zeros. So for example, all less than 10 magnitude, I put them as zeros. By then what I can do with that, what I can do, only say 50, okay, non-zero locations of the frequencies where I have information, remaining all are zeros. So I get a very good compression ratio in the sense that I, instead of representing 1,000 samples, I can represent 50 samples. Okay, but there is a loss, some loss. Okay, so if we can, in that case, we can't get the whole information. Same is the case even with, we will discuss with in view of with respect to CNNs what happens in compression. I may not discuss on compression, but I will discuss on, when I discuss on something like autoencoders. Okay, I will give a
Okay.
yeah. But
Okay,
it
sir.
is in conventional case. Yeah. Any
Okay,
other
sir.
question?
Thank you, sir.
Yeah, thank you.
Thank you, sir. Thank you very much.
Okay. Fine. Now, so let's move on now with the also with I will give a brief details of neural networks. I will not go into the details because I hope those are already discussed or you are familiar. And convolution neural networks also I will not be spending too much time. I will give only the pointers which I would like to highlight, which probably may not be very trivial. Even if you listen to some of the video lectures online or which are not directly available, okay, in the conventional teachings or discussions. And then I will move on to the other topics of convolution. Of course, if I want to bring in a machine learning method for making inference, as I mentioned, computer vision used to deal with the making inference from images or videos. Okay, so if I want to make inference, what are the essential steps? Assume that here is an example. Okay, we want to identify the fishes are coming on a conveyor belt. This is a classical example from Buddha and Hart. Fishes are coming on a conveyor belt. I want to automatically classify two kinds of fishes. Okay, so Solomon and sea bass are the two fishes. Okay, we want to put Solomon fishes on one side and sea bass fishes on the other side. Okay, that is the objective. So now how do we do this automatically? Is the question. The fishes are coming on a conveyor belt. Any quick answers? How do we do that? What should we do?
Take some image.
Yeah, fine. See, the very important thing when you go into the practical aspects, especially either in your research or in your industry, is to think more practically. Okay, so you can't get a problem of data set like online data sets. You have very nice data sets with thousands of images, ImageNet or whatever, like millions of images, and you also get a model from GitHub. Okay, of course, model from GitHub can be obtained, but the data set will be in very raw form. Okay, or the problem itself will be very very close to real scenario, not to the ideal scenarios or the. So now let's come to the now fishes are coming on a conveyor belt. That's where we are. Okay, we have a camera here capturing the images. We have an image like this. Okay, what is the next step?
We can segment that.
Yeah, we have to separate each fish. Okay, so first we have to identify the region of fishes first. Okay, so I want to say that this is the region of fish. Okay, so first I want to identify the regions of fishes. And then this region. So of course I may find edges, okay, or some method, okay, and then identify the region of edge. Okay, then I have segmented the fishes. What is the next step?
It is,
Next step is what?
you can find the area of,
Yeah, I can find the area, I can also find the length, I can find the width. So we want to extract features, right? So before feature extraction, do you want to do anything else?
pre-processing.
Yeah, what other pre-processing?
We can like rotate the image.
Okay, we have to rotate. Okay, so the reason is, see this, the reason is this fish will be like this, another fish will be like this, and so on. So if you want to extract length, see this is the reason we get, so it is not very easy. So first if we align it, all the objects, then we can get the better features. We have to align them and then only extract the features. So we align them, that's all comes under pre-processing. After that, finding, say for this application, number of fins, okay, the length, width, intensities, average intensity, all this can be features. And then perform, based on these features, you apply a neural network or support vector machine or so decision trees or any other classifier to classify. Okay, this is the conventional setting of, okay, making inference from an image. Okay, now we will see subsequently that this can also be done very efficiently in convolutional networks, but essentially this is how is usually done. Okay, now the problem here is, see, one of the problems is different modalities are even in same modality of images. Different applications needs different features. Okay, which features to extract is a challenging problem to or domain specific problem. So if there is some method which extracts features, okay, in a better way for most of the applications, that is more welcome. Okay, so similar is the case. Audio will have different, these are usually those who work on speech or audio. Okay, Bell spectrum or short and Fourier transform, okay, kind of features. Okay, which are more important, frequency based features are more important for audio. Similarly, text has different features. Okay, we will see that how CNNs will have an efficient way of extracting features in all these different modalities. Also, essentially, what's the neural network? So it mathematically, when you model, okay, it has of course neurons and the interconnection between neurons and synapses and dendrites. Okay, you have for a single neuron, you get inputs from several other neurons. Okay, and all these inputs, okay, it will assimilate and takes its own, gives own importance in terms of its weights. Okay, and then aggregates and gives a firing or non-firing action. Okay, so weighted sum of all inputs is taken as the net value to trigger or not to trigger the output. Okay, in a neuron. This is how it is mathematically modeled. Hope you are familiar with this. And what is the problem in learning a neuron? If I want to learn, that means a neuron for a particular task. What should I do? I have to, I have to
update the weight.
I have to identify the weights which will work for that application. So if I want to classify red blood cells and white blood cells, only binary classification. Assume that I have given the patches, okay, 20 cross 20 patches of cells. Okay, cell can be white blood cell or red blood cell. In that case, what do? I give each patch. Okay, I take the, let's say 20 cross 20 means 400 inputs. Okay, and then 400 weights I initialize somehow. Okay, randomly we initialize usually. Okay, with both positive and being negative. Okay, we initialize them and then want to, if I see at a first stretch, all white blood cells doesn't come with a label of 1, all red blood cells doesn't come with a label of 0. Okay, so we want to update this weight such that, okay, all red blood cells will have a label of 1 and white blood cells with a label of 0. How do we do this updation? Or how do we, this is called learning in neuron. Okay, learning is essentially identifying the weights that fits for that application to give corresponding labels for the input images. Okay, so now how do we do learning? What is the very well-known method for learning? Gap propagation. Okay, so that's fine. It is essentially gradient descent. Okay, we apply gradient descent to update the weight elements. Okay, so now what the limitation of a single neuron?
Non-linear.
Yeah, it can only give a linear decision boundary, being that this itself gives a W transpose X, W1 X1 plus W2 X2 plus B equal to 0. Line is what it says as the decision region. All one side is positive, all one side, other side is okay, other class. So it only can give a linear decision boundary. Okay, it can't give non-linear decision boundaries. So it can't solve the complex classification problems. So, for example, the XR problem is classically used. So there, what do we do now? So we want to pool several neurons. Each of them will use linear decision boundaries. Either combine them in a linear fashion or a non-linear fashion. Okay, to get a better decision boundary. Of course, we need to combine them in a nonlinear fashion, or we have to have a nonlinear combination of a linear combination of nonlinear decision boundaries. Okay. So essentially, as you can see here, you have multiple neurons. Each of them is giving some decision boundary. What is this saying? In this region belongs to one class. These regions belongs to other class. Okay. So that's where the need of neural networks comes. Okay. And neural networks is essentially needed to combine in a nonlinear fashion the several the inference from several neurons. Okay. And there are several architectures for putting these neurons. This is very well known architecture of feed forward neural network. Okay, wherein you have a set of inputs here. What essentially are these inputs? Usually, what are the inputs? Features. Okay, feature values. If I take intensities itself as the features, okay, then the intensities of 20 cross 20 intensity values 400 cross 1 is a feature vector. Okay, instead, if I take histogram of orientation gradients, okay, I can. It depends upon how many features I get. Okay, for 20 cross 20 image, I may get say 50 cross 1 feature vector. Okay, the length and width and a few 5 features if I take in a specific application, those 5 will be the features. Okay, so I give this and then I try to get what are the output expected outputs. Yeah, if I have 10 class classification, digit classification, for example, or 26 character recognition. So essentially alphabet classification. So those many the number of outputs will be here. Okay, and then what are these input layer and hidden layer and output layer? Okay, so and then what do we do here? What is the difference between learning a neuron versus learning a neural network? Essentially, we have output only here. Okay, we don't have at each neuron. We have output only here. Okay, and we have target values only here and outputs only here. We get the error from here. Okay, that's where the name back propagation comes. Error back propagation. We have error only here. We want to back propagate to adjust all these weight elements. Similarly, all these weight elements. Okay, and then we want to do that for each of the training sample. Okay, and we want to do for all training samples. If we complete over all training samples, we say that one epoch of training is completed. We go for another epoch and so on, or we randomly sample. Okay, and then do training of all these weights. And the weight adjustment is essentially done by taking derivative of the loss function with respect to corresponding weight element. Okay, I hope you are familiar. Otherwise, I would suggest I have taken this from Dudanha. So otherwise, I would suggest that you can get a more details of it. It is very essential to understand the learning aspects of neural networks and convolutional neural networks as well. Those who are working essentially in this field. So I would like to give one input highlight. If you have captured this, is very good. Otherwise, this is the key for learning in neural networks. See, if I am updating this weight. Okay, so I assume that I am updating this weight element. Okay, let's take this weight element. Okay, I am updating this weight element. What essentially I get dose away dou w. Okay, 1 2 if I call this as okay, or 2 1 if I call. Okay, dose away dou w 2 1. How do I get it? Okay, if I want to tell in verbally, what I do is after doing all derivations and so on, I take the input from here, I take the error at this location, multiply both of them, that will be the delta w. Okay, so that means if I want to find dose by dou w, that is delta w, to update this corresponding weight, what essentially we do is up to here, I might have back propagated. There will be some delta net 2 here. Okay, delta net 2 multiplied by y1 will give me delta w21. That's all. Okay, this is the key observation. What I would suggest is in your derivation, you correlate this. Whether is it happening at each layer and each neuron or not. Okay, from the expressions. Okay, delta wji if you do, delta wji means delta net j into y. That's all here. Okay, now similarly, if I want to update this weight element, okay, let's take now this weight element. This is x2 to delta net. See here delta net 1 I call. Delta net 1 h matter. Now if I want to update this, delta w here. W12, if I want to update this, what should I do now? How do I get this update? Simply Multiply this delta net here, delta net 1 into x2. That's all. That's all. Okay. This is the key for learning in deep neural networks. Otherwise, the back propagation that we conventionally do, dose A by dou W J, and then by chain rule, if we start doing, okay, more than 2 layers, it becomes too much cumbersome. Okay, and we can't apply chain rule that easy. Of course, people use computational graphs for doing that better. Even in computational graphs, what is actually done is to do according to this. That means we get the gradients at all locations first. Okay, we just back propagate first delta W. Deltas we get first. Once we get the deltas, we take the delta W or the weight. If you want to update, see the weight update. Simply take the error from rear end. Okay, input from the front end. Okay, and then multiply. That's all. Okay, so that is what is done. Also in learning. Fine. Also hope. No, yeah.
Can you draw that?
Yeah, fine. Okay. Yeah, probably you can take a. Okay, I will give since it is I am telling about any arbitrary neural network. Okay, with different layers. So I am just writing here like this. Okay, so assume that all connections are there. Okay, I will not be drawing all connections, but assume that this is all there. Okay, of course, this is also represented in different ways. So people represent in this way as well. Okay, of course I want to highlight the neurons. So I have written in this way. So I will just do like this, but assume that all interconnections are there. Okay, which I hope you are familiar with, right? All interconnections are there. I will take only the one which I want to highlight. Okay, so here and then here, of course, the output. So I can have any number of layers here. So now if I have here, okay, O1, O2 and O3, assume that, and T1 and T3 you have here. Okay, J is essentially summation over OI minus Ti. Okay, what is that? Assume that mean square error is the cost function here. Okay, whatever. Fine. Now what I want to do? I want to update this particular, neuron weight. Okay, I call this as W. Okay, here it is Y1, Y2, and this is a net. Okay, then this, it is first layer. Okay, second layer. Okay, net 2 or net 3 or net 2. Fine. Okay, net 1 I call it here. Okay, net 2 of 1. Okay, so you can see here, right? So what I do now? Initially, if I want to get net 2 of 1, what I do? So this net value initially, if I want to get, okay, net 1 of 2. If I want to get initially, what I do? It is weighted sum of all these elements, right? So W, if I call it as Ji here, okay, summation over Wji, okay, into Yj, okay, J ranging from 1 to whatever 3 here, okay, will give me, or if I put this as 1, J is also 1, okay. So this is essentially f of this, will give me the output plus bias, of course. Okay, in the forward pass, this is what I am doing, right? In the forward pass, what I am doing? Here, this net value comes as a weighted sum of all these inputs and weights. Correct? Okay, all these weights up till, right? So this is in forward pass. Now what I am telling is, I want to update, okay, delta W2, okay, sorry, 1, 2, or delta W1, 2. This is what I want to update. That means, okay, so dou J by dou W1, 2, I want to find. Dou J by dou W1, 2, I want to find. Those are my I want to find. What I'm saying, this simple trick is I already have error here. Okay, delta O is here. Okay, delta net. Okay, net 4 is here. Okay, delta net 3 is here. Okay, delta net 2 will be here. Okay, net 2 will be here. Okay, I can back propagate, right? Delta net 1 is here like that. Okay, I get the errors, right? So essentially, back propagating means if I cross the activation function here. Okay, so activation function, if I am crossing F dash, I multiply it. Okay, if I am crossing in forward pass, I will be multiplying with W. So in the reverse pass, it will come as W transpose. Like that. Okay, so essentially in the forward pass, I will be getting net 4. Okay, is equal to W times net. Okay, sorry, net 3. Oh, that's all, net 3. Okay, in the forward pass, it will be like that. Okay, all these net values, if I have after net values, I will get Y values, right? So Y3, okay, Y4, right? y4 is equal to f of net value. See, what net value I am calling is just with summation, the value is net value. Okay, with activation, the value is y value. Okay, that's what is my notation. So y4 is equal to f of net 3. Okay, that's our notation there. Okay, so of course I have used net index and y index separately, so hope you can understand. And here it is essentially y4 is equal to w into instead of net here you have w into f3. Okay, if you have sorry y3. Okay, yeah. So here it is net 4 is equal to w into this w into y4, right? y4 how do I get? F of it, like this, right? So I hope this is clear, right? So y3 means y4 means okay f of this net value. Okay, so you want to have same notation for y and net. If you want to have this, let us call as net 2 directly. Okay, and then net 3. Okay, and then net y4. Okay. Okay, then in that case, y4 here is equal to, okay, and then this net 5. Okay, so net 5 is equal to, in forward pass, it is w into y4. Okay, you use this y outputs, okay, multiply with this w, you get essentially, okay, net value, that's all. Okay, this is in the forward pass. Okay, in terms of expressions, this is what we are doing. Okay, so now in the reverse pass, or when we want to find gradients, what I am telling is delta W21 here. Okay, so essentially in this W1 we call all set of weights W2, W3 and W4 here. Okay, so now what I want to adjust is at this layer, right? So W2 of this. So W2 of this is what I want to adjust. Now what I am saying, essentially you take this net value, okay, and then this input delta net value here and then input here, multiply, that's all. Nothing else. So it is essentially delta net value of what I should use? Delta net 3 of 1. Okay, delta net 3 of 1, which is the error R gradient here. Okay, multiplied by y2. That's all. Or in matrix form, if I want to take, okay, delta net, okay, 3 into y transpose. That's all. Okay, y transpose means y2 transpose. Okay, take my subscripts and superscripts. Based on the understanding here, okay, but this is what is done. That's all, nothing else. Okay, so if you want to adjust the weights, take the all inputs here, take all gradients here. Okay, just give this gradient set of gradient vector into input vector. That's all. Transpose of input vector. Okay, that's how it is done at each layer. That's all. So you take any layer first, just do okay gradient updates. Okay, at each layer and apply this. That's all. Okay, that is conventionally done through computational graphs. Gradient updates are conventionally done through computational graphs. But this idea of multiplying the gradients with the inputs is key to capture that at any layer I can immediately update the weights. If I want to update the weight here, okay, once I do gradient delta values, if I find, I no need to do from all through here. No need to apply chain rule. Directly take the delta here, input here, and multiply. Okay, fine. So this is done in deep neural networks. That means what here, one thing I would like to highlight is the process of updating the weights is exactly similar. Either you do it in the first layer or at the 10th layer or at the 100th layer, okay, or at 1000th layer. The way of back propagation is also similar because you have anyway weight elements here, okay, which are multiplying operation, okay, activation function, which is in forward pass activation function, reverse pass f dash, okay, and then that's all. One summation, one activation, one summation, one activation. So if you know how to back propagate through a activation function, f to f dash, okay, f in forward pass, f dash in reverse pass, okay, w multiplication in forward pass, w transpose will come as in reverse pass. That's all, nothing else. So in forward pass, you multiply w f, okay, w f, like that it will go like this. Here f dash, w transpose, f dash, w transpose, it goes like this. Nothing else. Okay. So it's all same process repeated at each layer. Okay. So only thing is dimensions has to be taken little carefully and properly. Okay, when you want to really put that into framework. Okay, so I will move on here. So this is how it is done in deep neural networks. Of course, understanding of what neural networks does. Hopefully, you might have seen it. Okay, what it does is essentially it. So if I take a single layer, okay, we assume that this is not even 2-layer, 1-layer network wherein I have features. Say this is assume that this is 30 cross 30 image. Okay, and then I am directly getting 10 labels. Okay, so in fact this is CFAR data set with 32 cross 32 input. But let us assume that 30 cross 30. Okay, and then you have output as and 3 channel. Here 3 channel is also there. Let's assume that 30 cross 30, there is 900 cross 1 here, and output is 10 labels. That means you are classifying to 10 different classes. Now, what essentially this neural network learns, okay, if I want to see, what it learns is, say if I give a car class, okay, sample, after once I complete learning or training neural network, if I give a car sample, okay, it has to say it is a car. Okay, if I give a bird, it has to tell bird. Okay, something like that. Now, if I see a neuron corresponding to car here, assume that third class is car class. Okay, let's take a neuron corresponding to car class, third neuron here, and it is connected to how many input neurons? 900. Okay, because it is 900 cross 1 to, okay, 10 cross 1, direct 1 layer. That's all. Assume that I represent somehow with 1 layer. Okay, so this one of the output class is connected to all 900. If I see all the 900 cross 1 weights, okay, corresponding weights, that weight vector of 900 cross 1, there will be 900 cross 1 weights, right? If I put it in 2 cross 2 image, okay, that is in a 30 cross 30 image, okay, then what will happen? It looks like an image. That essentially looks like an average version of car, right? So what is it doing now? It is, if I take a neural network, okay, with assume that somehow I model with a, okay, 900 cross 1 here, okay, and then 10 cross 1 here, okay, and all are interconnected. So this W matrix now I represented as 30 cross 30. Okay, and if I visualize as an image, okay, from a particular output, so this is the car class. Okay, so from a particular output, it is actually 900 cross 1. Okay, so otherwise this whole W matrix is, okay, whole W matrix is how much? 900 cross 10, right? In that I have taken W3. Okay, W3, that means third column of it. Okay, I have taken and then I represented it as, okay, 30 cross 10. And that looks like an average version of car. So what is that learning now? What is the neural network learning? If that is the case, what is that neural network learning? Okay, if you see all interconnections, they are all, what is it for a particular class, what is it learning? It is essentially identifying the correlated features. If I see all this, okay, so it is from each of the features, okay, it is with all the samples of cars, okay, it is finding the correlations, the filter, okay, that is a best match for all these samples is what is it learning. Okay, so if I consider this as 30 plus 30 filter, now, okay, car filter, okay, or car kernel, okay, this is learning a kernel, okay, representing car. Okay, right? So it is essentially identifying the features or template. It adds and the kernel. Okay, that matches across all samples of car. Okay, similarly, if I take this is some bird or something. Okay, it learns a bird. Okay, so like that. Okay, that's what essentially we can interpret. Okay, in a simpler cases.
Can you say that neural network is a kernel learning mechanism?
Yeah, essentially it is doing that. Oh, it is learning in a slightly different fashion. Okay, so but if I want to apply this neural network for a very, say the limitation why the neural networks didn't became famous, okay, again till 2000s, okay, is they were very quite famous and used in 1980s to 1990s, okay, in all applications. but beyond a point, their accuracies were not very good, or we cannot. In fact, they are almost as similar to support vector machine or any other classifiers, decision trees, and so on. Okay, but the one of the bottleneck is developing deep neural networks. If I train a neural network over 10 layers or 50 layers, okay, what will happen is, see, as we have seen here, at each layer there is one f dash multiplying. Okay, usual activation function that people use is sigmoid activation function. Okay, sigmoid activation function ranges from 0 to 1. Okay, and f dash of sigmoid activation function, derivative of sigmoid activation function ranges from f dash ranges from 0 to 0.5 only, because f dash of net, okay, in a sigmoid is equal to f of net into 1 minus f of net, okay, which is 2 times of say sigmoid activation function range. So it essentially is in the range 0 to 0.25 only. Okay, so you can't say each time you are multiplying with 0.25. So what will happen? It is okay. It essentially the weights, whichever error you have, will get damped too much. Okay, by the time you reach to the initial layers. So you cannot have a good weight updating mechanism. Okay, after 5 layers. Okay, it will be say 1/4 of this, 1/4 power 10. Okay, if you came, okay, come back by 10 layers. So you can't use sigmoid activation function. That is one finding people had. Okay, and they replaced it with railway activation function. Okay, rectified linear unity activation function, which has gradient in negative direction, in negative region. The gradient of ReLU is 0. In positive, it is in positive region. ReLU is it is rectified linear unit, right? Activation function itself is rectified linear unit. Okay, it has like this. Okay, so it is 0 here, it is here 1. Okay, so this is net value and this is f of net value. Okay, so essentially what rectified linear unit does is it has 1. So you put thousands of layers, doesn't matter. Okay, of course it has a limit of, you need non-linearity, that's why you have put here, okay, 0. And it has its own difficulties and so on, but it's good. It's good in terms of developing deep neural networks. So the other, see now this is you can of course develop deep neural networks, okay, feed forward neural networks. But the problem, one more problem with feed forward neural networks, in fact this is the key development for convolutional networks and the era of all deep learning methods. The data cannot be represented in its own dimension. Okay, so you have to bring in with one-dimensional features and perform some kind of machine learning. Okay, in a conventional setting, which is a very important bottleneck, because if you want to classify faces, okay, I can't see the face features in 2 dimensions, or I can't see the face in 2 dimensions and take a decision. You only need to bring in 1 dimension and then take a decision. Okay, it's a very spatial information is completely lost. And if I have a 3D data, okay, I want to see all 3 dimensions and decide. I can't do that. You have to bring into 1 dimension and decide. So, and the associated problems, if there is a small shift happens, okay, then what will happen? When I want to bring to 1 dimension, okay, small shift, 1 row shift means the vector that I get with 1 row shift will be quite different from without row shift. Similarly, column shift. Okay, so bringing all rotation, all this has a implication on bringing data from its own spatial dimension to or its dimension to 1 dimension. So these are not invariant to many of the geometric and spatial variations. Okay, so then the advent of convolutional network came, and the idea there is, so like we do in convolutions, operation for feature extraction in images, okay, can we also use this principle of convolution in neural network setting? Can I learn a 2-dimensional filter, okay, rather than just using correlation in 1 dimension and try to get an average weight elements? Okay, can I do a filter directly or 2-dimensional kernel or multi-dimensional kernel? Okay, that essentially extract features, okay, in a learning setting. That means I don't want to prefix the filter, okay, but I want to learn the filter. But the filter should be in its original dimension. Okay, it can't be in 1 dimension all the time. So then the idea of learning, and it can learn the features, okay, in a layered structure, okay, like we have in neural networks. first learn gradients, edges, okay, low level features, learn little high level features, combining them, and so on. Okay, so this is essentially done in convolutional neural networks. And this architecture, hope you are familiar. This convolutional neural network, DNet architecture, and this is the first convolutional neural network. Okay, and essentially the beauty of this is it has only two different operations, like we have in feed forward neural network. Okay, you have not many operations here. Just a matrix vector multiplication and a nonlinear activation. Okay, and same is the case with each layer. Similarly here, you want feature extraction through convolution. So convolution operation is needed. Convolution operation is essentially what? Element-wise multiplication and summation. Exactly what we are doing here. We are also doing element-wise multiplication here with x and w. Okay, and summation you are doing here. But instead of in one dimension, in CNNs you are doing in 2 dimensions or multi-dimensions. Multi-dimensional convolution and summation. Okay, summation is essentially part of convolution. Okay, multi-dimensional summation and multiplication and convolution, addition. Okay, that is convolution. And once the convolution is done, but the problem came is, see if I keep if I do one set of convolution, I extract one set of features. Okay, I want edges. Okay, I also want key points. I also want to highlight, okay, transition phase, say for example, for bright to dark regions. I also learn some other features. So each kernel will give me only one kind of features or one set of features. I want to get several sets of features and assimilate all of them and make an instance. So what is done is convolution operation, of course, gives feature extraction, does feature extraction. But I want to have 6 kind of features, 6 sets of features. Develop 6 filters. Okay, assume that there are 6 filters. Okay, which will extract, each will extract different features. But other problem is once I extract features, okay, that is not enough. Finally, if I want to do classification, for example, I have to assimilate all information, right? And then take a decision. See, if I already have 100 cross 100 image, assume that. Okay, I did one with some 5 cross 5 kernel, I have done a convolution. Another, roughly it is also of dimensions 100 cross 100. Okay, like that I have 6 filters. 6 filters and 6 feature maps, we call this. 6 feature maps, each of them are getting 6 into 100 cross 100. And then I may not be confine myself to extract only low level features or basic features. I want some high level features. So on the top of it, I want to do another 6 kernel, another 6 or 12. Okay, I want to extract another set of features. Okay, I want to keep doing that. Okay, for several layers. Then I am increasing the number of layers. Okay, increasing the computations and having it 100 cross 100 into those many dimensions. Okay, those many operations. So it will be too much computationally complex. And also, finally, I want to assimilate all, get only one inference like yes or no kind of things. Or, okay, 10 class classification or whatever classification. So that information is not, we have to represent that information also compactly. Okay, then the concept of pooling layer or sampling layer has come. Okay, how do we compactly represent the information? Okay, that's what is done by pooling or sampling layer. So we have, I think you might have seen this in different slides. This is the convolution operation. Okay, so this is element wise, you put the kernel and multiply at each location. Okay, and then get the final values. Here, one thing that if you want to understand the papers or the architectures, okay, in this area, what you should be familiar is if I take a particular input dimension, okay, and if I take a particular kernel, what will be the output dimension? Okay, under different conditions. Okay, sometimes convolution is done like this. Sometimes convolution is done with a stride of 1, stride of 2. That means I shift, I jump it. Okay, I don't do at each element. Okay, or sometimes I pad with zeros. Okay, in different scenarios, what will be the dimension and output dimensions? Okay, but essentially the convolution operation is done, and it is done in different ways. If I work on speech processing or say some kind of one-dimensional data, time series analysis data and so on, convolution is done in 1 dimension. Okay, if I work on image processing mainly with say some input and output in 2D. I may do 2D to 2D convolution. This 2D to 2D convolution. As you can see here, see the kernel here is having non-zero values here. Okay, here it is non-zero value. Here it is overlapping is 0, so output is 0 here. Okay, so here output is 3 here. Okay, like that. So this is the convolution operation. So this is 2D to 2D convolution. As you can see here, input is 2D, output is 2D, where kernel is moved. Okay, this is what convolution? 3D to 2D. Essentially, when I already have 6 maps, feature maps, okay, later if I want to get only single feature map, one of the feature map from the 6 feature maps, what I do? 3D to 2D convolution I want. Okay, so I have all feature maps here, assimilate all information, get one map here. Okay, so that is 3D to 2D convolution. And in some applications, okay, I want, of course, this is 3D to 2D convolution. And in some applications, I want to do 3D feature maps to 3D feature maps. Essentially in 3D object detection or, okay, 3D reconstruction kind of applications. Okay, I want to do 3D to 3D convolution. So there, the filter is also having 2 dimensions, like 5 cross 5 cross 3 or something like that. Okay, it will be scrolled across both spatial and depth direction, channel dimension. Okay, so these are all different ways of doing convolution, but all are for feature extraction. Okay, in that respect to domains and respect to networks. And the sampling layer as what is the key role of sampling layer, subsampling layer, is to compactly represent the information of features, okay, that are extracted through convolution. As you can see, for humans, okay, also you see that this and this, if you see, we can't really say it is A, but yet this, okay, it is very difficult. Okay, but here it is reasonably simpler. So when you compactly represent, the information is also is not lost. Okay, major information is not lost. Okay, so that's why people use in the neighborhood, which is the maximum information I would like to put here. That is referred to as max pool. Okay, so they pool the information of 4 pixels to 1 pixel by using averaging operation or maximum operation. Okay, and so on. This is pooling by average pooling or max pooling or whatever. Okay, so these are the essential steps of a neural network, convolutional neural networks. And one more thing that you should know is, if you want to generate from 6 maps to another set of maps, 12 maps here, how do I do? Okay, so as we mentioned, this is already 12 cross 12 cross 6. Okay, so this is actually in 3 dimensions. I want to get a map here, one map here, like that 12 maps I want to get. So I may apply 3D to 2D convolution to get one map. Okay, like that with a kernel of 5 cross 5 cross 6 now. Okay, similarly here, if I want to get 12 maps, 12 such kernels has to be there, right? That means 12, we have here 5 cross 5 cross 6 into 12. Those many the color elements. When you want to understand papers, other important thing is, if you are given one layer and other layer dimensions, you should be able to figure out, okay, what essentially is the kernel dimension. Okay, how many kernels are required? Okay, what is the kind of convolution happening? Of course, now there are several ways of convolution as well. Okay, you know, conventional convolution is anyway discussed. You have dilated convolution. Okay, you have many other convolutions, deformable convolution, many other convolution. But conventional way of doing convolution is through whatever we have discussed. So other thing that probably with that we can take a small pause, either for questions or for small 5 minutes break. Other thing I would like to highlight is the back propagation in convolution neural networks. Okay, so now what is happening in convolution neural network is, we have some set of features here. Of course, we start with a 28 cross 28 image. Okay, I am taking with the linear architecture with a this is MNIST data set for digits. Okay, having 28 cross 28 input. And the next, you have 6 filters. Okay, 6 feature maps. Okay, with 6 filters. And then you have the next, we are doing a kind of a subsampling, downsampling by 2. Okay, subsampling by 2, either through max pooling or average pooling. And then we are doing another set of convolutions to get maps. Okay, and we are doing again pooling, and we are then what we do, we concatenate all these features, okay, and into one dimension and take that for okay learning like a feed forward neural network structure. Okay, so after a set of convolutions and pooling, what CNN has is to get a one dimensional representation, okay, of the aggregated feature information and learn like a fully connected layer, okay, to classify. Now errors are here. Now what we want to do is we want to backpropagate these errors to adjust all these weights, adjust all the kernel elements, okay. Why we want to adjust kernel elements? Because we have not set them, okay. That means we are not saying that edge kernel we use or corner kernel we use or okay whatever kernel. We want to learn such that it maximizes the classification score or the classification of different classes. So we want, that is essentially is the difference between conventional methods and convolutional neural networks. Okay. So we want to find the error and backpropagate all the weights and kernels. Okay, that is the objective. Now, how does that done? Okay, let me give a kind of a small picture. See, you at the fully connected layer. Okay, what is done? Anyway, you have a fully connected. Say you have this outputs. Okay, this is a weight matrix. Okay, you know how to update these weights. Now, from fully connected layer to okay, you want to go back and update these kernel weights. So if I have done a kind of a 2D to 1D, okay, only reshaping here, the gradients also, the delta values also gets reshaped, nothing else. Whatever is the forward operation, that determines the back propagation. That's all. So here, if I am just taking the values, whatever input values and then put into one dimension, delta values I take here, put into two dimension, nothing else, no change. Now, let me go back. Okay, so here, what I do here, at each convolution layer, okay, let me see where the equation is. Okay, at each convolution layer, what I do a convolution operation, element-wise multiplication, and take an activation function. I have not taken, of course, activation function here. Okay, of course, I add a bias and take activation function, right? So this is essentially the convolution operation. At a convolution layer, this is what is happening. Okay, now I have delta values at this S2. Okay. This is at convolution layer, but this is from convolution to downsampling or pooling. See, if I am doing convolution to subsampling. Okay, what I am doing, 8 cross 8 I am representing as 4 cross 4. Okay, so I have delta values of 4 cross 4 already here. I want to get at 8 cross 8. What do I do now? If I am doing downsampling in the forward pass, what I do in the reverse pass or in the backward pass? Upsampling, that's all. Okay, so downsampling here is essentially upsampling. That means if I take 4 values here and average them and put one value here, what I do, I take the delta here and put at all 4 locations. Okay, delta by 4, I put at all 4 locations. That's all. Okay, so what I do is essentially whatever is the forward operation, I put as reverse. So I am putting 4 values and putting maximum here. What I do, delta, whichever is maximum, I put at corresponding location of maximum value. Remaining all I put as zeros. That's all, nothing else. Right? So, in the back propagation at the sampling layer is essentially a downsampling to upsampling. Right? Right? And then now we want to, here, this is a convolution layer. Okay, from the sample, from the 12 cross 12 to 8 cross 8, I got through a convolution operation. Now, this is convolution operation. I have delta values, delta C already is here. Now, since I did a convolution operation in the forward pass, it turns out to be, the back propagation turns out to be correlation, that's all. Okay, so like you have seen here, okay, wait, forward pass W means revert pass W transpose, right? Okay, like that, if you see forward pass convolution, reverse pass becomes correlation. Okay, of course, I will show some visual details of it. Okay, that's all happens. After that, again, sampling, so downsampling, upsampling we do, okay, and then convolution, and then correlation. That's all, nothing else. And wherever we use activation function, F forward and F dash backward. That's all. Okay. So now let me give a picture of why convolution becomes a correlation. Okay. And we can conclude with that. This session, current session. So this is what essentially in terms of equations. This is F dash. Okay. And and this is error, this is f dash, okay, and then w into f. So W transpose essentially is this, okay, into delta, and here you will see f dash and upsampling, okay, of these things, reshaped version of this, okay, and then again here these deltas and correlation with the kernel elements, okay, and upsampling this and f dash. That's all. Okay, this is how it happens. Even if you have hundreds of layers, same thing happens. Okay, upsampling at sampling layer, okay, in the backpropagation, and correlation instead of convolution with appropriate dimensions and other things. Okay, and f dash for f. That's all. Okay, so I will skip the other small details. And as you can see here, this is a visualization on how exactly you do convolution operation. Okay, this is y1 is obtained by convolution of this. Okay, putting this kernel at this location. You got y1 here. Okay, y2 you got by putting at this location. y2 here. Like that you got correlation result. Now I have got deltas here. Delta w, delta y1, delta y2, all these are with me. What I want to get is, okay, delta x's I want to get. Okay, in back propagation. Okay, I am going from this x to y, y to x. Now what I do, this kernel here, correlation if I do, essentially you can see that, see these equations if you write explicitly, this is what happens. y1, y2, y4. y1 if I write, y1 is nothing but w1 x. This is the key. If you understand this, I think remaining all are straightforward. y1 if you get, how do you get? w1 x1 plus, of course I am doing w9 x1 because I flipped it. Okay, w9 x1 plus, okay, w8 into x2 plus, w7 into x3 plus, okay, w6 into x5, all that is here, right? As you can see. Now, if I want to get delta x1, okay, delta x1, I need to see in this where all x1 is involved. See where all x1 is involved. Here it is x1 is involved. Where else x1 is involved? X1 is also, no one x1 is involved. So delta W9 is simply is equal, delta X1 is simply equal to W9 into delta Y1. That's all. Okay. So in forward pass, if there is a connection, okay, as I mentioned, okay, the error at the rear end, sorry, delta W9 if I want to do, then it is whatever I have mentioned. So here essentially we have to see delta W5 if I want, sorry, delta X10 if I want to do now. Delta X10, which way I want to see in this where X10 is involved. Okay, delta X10, where is it involved? Here it is involved. Here it is involved. And where else? Here it is involved. Here it is involved. So delta X10 is equal to what? Delta Y1 into W2 plus, okay, delta Y2 into how much? Delta Y2 into W3 plus delta Y3 into W5 plus delta Y4 into W6. That's all. Okay, is delta X10. Delta X10, if you see, okay, delta X10 is delta W6 into delta X10, right? Okay, delta Y1 into W2 plus delta Y3 into W5. Okay, delta Y2 into yeah, it's still right. Delta Y2 into W3. Okay, like that. You can see this, right? So that's how it happens. So in the forward pass, whatever you have, based on that, you can write like this individual equations. This, if you see, hold together, it is nothing but the correlation operation. Okay. So this exercise is being done by one of my PhD students. So if you want to really understand how correlation and convolution are, okay, forward, backward passes, you have to do that operation or exercise. Okay, so this is essentially same is the case even when you want to update weights. Okay, as I mentioned, delta W if you want to update, you have to see in the forward pass, this is the convolution operation. In the forward pass, delta W1, where all W1 is there? Where all W1 is there, you can see. The W1 is, I think this, you are not able to see well, right? W1 is not there anywhere. Oh, surprising. W1 is there. So I think our this projector is not able to distinguish between W1 and W4. But W1 is there with all this. Okay, so essentially it should be there. Okay, Y4 it is with where it is with X25. Y4 X25 somewhere. Okay, so it should be there like that. No, so it will be there. So I would suggest that you can do this exercise. Of course, in the slides it will be clear. Okay, you can see in the slides. But if you want to understand, you should do this exercise. So what it finally extracts are good features. Okay, after learning like this, okay, reasonably good features, which are to some extent can be visualized. Okay, so we will stop here, give a break here. If you have any quick questions, we will discuss them, and then we will take a 5 minutes or some
15 minutes.
15 minutes. Yeah, we can take 15 minutes. Any questions or doubts? Okay, from online people. Okay, fine. So we'll, yeah, please.
So regarding these kernels or CNN, these layers, initially it's randomized. Kernel weights are randomized,
Correct.
and so as we move backward and forward, how are these
Okay.
developing into these different kernels actually?
Yeah, right. Yeah,
How are they actually transforming by itself? Right?
Yeah.
We don't do anything over it.
correct.
What is the magic?
Yeah,
I
sure.
feel it as magic. Right?
Yeah, right.
So how is it actually happening?
Yeah, fine. Good. So I will discuss. So online participants, are you able to listen to our discussion here? Because I am standing there and talking, right? Online are there?
Yes, sir. Yes, sir.
Yeah.
They can able to release it.
Okay,
They
yeah,
respond.
good.
They respond.
Thank you. Yeah, sure. So essentially, see, one key aspect is we are controlling from here. See, we are setting an objective function, saying that you are. I'm adjusting all these weights with a objective function, and this is essentially mathematically directed towards that. So that's why they get aligned or they get adjusted, such that, say, if I see, of course, in gradient descent discussion, as you can see, if I keep adjusting the weight, the element, it reaches to the minima, right? Minima in the cost function means that for all class 1 samples, it gives a label of class 1, and class 2 samples gives a label of class 2. That's what is minima. Of course, max, it gives optimally. In sense, for all samples, it may not give for 90% of samples and 90% of samples or whatever. Okay. Similar thing is even happening here. So that's why you can't see that these weights. See, for example, later some of the people visualize the weights or the kernels length as well. You can't see very clear structure of what kernels are being led, except in few applications where you target to learn a very specific filters and kernels.
So that particular filter kernel, so the defining the number of kernels over there has also great impact on the classification.
It does has, but not probably very great. Of course, the depth of the convolutional networks matters well, and effective backpropagation is what matters more. That means if the how effective are we in terms of backpropagating the error information or the reducing the error by backpropagation from across all layers. That's why now in the next discussion, I will discuss on key developments of CNNs. I will be again there. I will be highlighting few aspects which made this, and one of them is how effectively are we backpropagating the error information. Okay, that's and that is also there in terms of like whether how many layers can we go and how many channels can we go. That's a kind of a design choice, but more important thing is how effectively we can backpropagate the information.
So, in certain cases, can these filters be adjusted? So let's say, for example, certain filters can observe noise and things.
Yeah.
So by defaultly, those things get added over here, or can we work on such kind of things also?
Yeah, so there are some works essentially when even in evolution of GANs. So there are some kind of works where they want to make the filters learn in a particular way. Of course, even there are some initial developments as well, PCAnet, which tries to extract the filters, extracting the PCA kind of like principal information of the filters and so on at each layer. So like that, there are some works, but they are limited. Because the complexity is so high that guiding them is not very easy. Of course, at each stage there are, of course, batch normalization is one trick where we redistribute the information at each layer. So what we are trying to do is, I am saying the filter, usually filter values can be from -1 to 1, assume that. I want to put them, okay, in -0.5 to +0.5, or I want to specifically put them in some other distribution, completely change the distribution itself. Some such things we can do at each layer. But we can understand them either at a statistical level or at a few inferences at few layers. But across is difficult. Thank you.